Hey, let's look at section 5.4 here. It's just a quick note about definite and indefinite integrals to help keep our heads on straight. Basically, an integral is a signed area. We can also see an integral as being an antiderivative. And yesterday we looked at some area functions, or in the last couple of videos, some area functions that were defined by integrals. And we said, so I could put an A out here, I suppose, if we wanted, or a big F, whatever we want to use. But this function, this integral value function, that A is a function whose outputs are the signed areas under F, right? The signed areas under another graph. And then we can also say that this function, whatever we want to call it, is also an antiderivative of F with a particular C. So we're going to go ahead and look at kind of clarifying a bit about what that might mean. This is an indefinite integral. It does not have bounds. So I'll write that it's an indefinite integral. Okay, and if we find the antiderivative of little f, we get, we'll just call it big F plus C, right? These lead to very general antiderivatives. This is a general antiderivative. We acknowledge that there could be any constant there. So we're going to get kind of a family of graphs, and I'll give you a specific one here in a minute. And then if we integrate this that actually has bounds, this is a definite integral. Integrate little f, we get big F, right? But we can plug in the upper bound and the lower bound. Keep in mind that A is a constant, just like the ones that we worked with on the last couple of videos. And so we actually have a particular antiderivative, a very specific antiderivative, no plus C. Okay, because we have those bounds. All right, so let's take a look at a couple specific ones here. If we integrate 2x, we get x squared and then plus c. And you can plug any value in for c you want and then take the derivative of that, and you'll see you do actually get 2x, right? So x squared plus c is an antiderivative of 2x. And then if we want to graph those, just get a couple points here and try to connect the dots to the best of my ability. This is my little f. Okay, that wasn't great, but there it is. Okay, and then we're going to draw a big F, but it's just a family of graphs. So it could be just, this parabola. It could be this parabola. It could be this parabola. If c is like 2.5. If c is negative, we'll have parabolas down here. And so what we end up getting is a whole family of graphs. But this derivative does still tell us interesting things about its antiderivative. Notice when our derivative is negative below the x-axis, our graph is decreasing, has negative slopes. When our f equals 0, we have extremum. More specifically, our f is changing from negative to positive, so we have a minimum. And then over here to the right of the x-axis, our derivative value is positive, so the antiderivative has positive slopes. It's increasing. All right, let's take a look at this one, a very specific case. And if we find the antiderivative of 2t, we get t squared. And now we have bounds, so we can go ahead and plug those in. So we get x squared minus 9. Okay, upper bound minus the lower bound. Now that's a very specific graph, right? So I'm going to graph our antiderivative again. Our f again, and then we'll graph the antiderivative and see if we can see kind of what this tells us. All right, so I think I can get down here to 1, 2, 3, 4, 5, 6, 7, 8, 9, and I know that my x-intercepts are going to be here. Oh boy, let's just hope Miss Weber can do this. All righty. Could have been worse, let me tell you. Okay, and then let's kind of talk about some of the specific information we get from this. Let's look at actually using this function like we did yesterday, or maybe not yesterday, but in the last couple of videos. What if we were to integrate from 3 to, say, 3? Okay, so we know that that value would be 0. So if we integrate from 3 to 3, we get 0. And what that means is over here, when I'll use big F of x, it's defined by as being the antiderivative. When we put big F of 3, it means we're getting 0. And if you look over here at when x is 3, y is 0. If we were to look at F of -3, we would be integrating from 3 to -3, this graph, the signed area under our graph of 2t. And if you look at integrating from 3 back to -3, you're going to get these triangles that have the same area, but one is above and one is below. So we're going to get a 0 when at -3 also. And if you look at our graph of big F, we do have a 0 at -3. And if we want to integrate, let's just say, find f at 0, that means we're going to integrate, if you look at our formula, from 3 to 0. That's just the signed area under this curve, and it would be from 3 back to 0. So the area of this triangle, which is 1/2 of the height, which is 6, so 2, times the base, 1/2 of 6 is 3, times the base, which is 3, that's 9, but because we're integrating from 3 back to 0, we're going to get a value of -9 when x is 0, and that's exactly what we have on that graph of big F. So we did a couple of these yesterday, and trust me, there's more to come, but the idea, and I'll just put a little starry here, is that your f of x values are areas, signed areas, under the curve little f, right? Between the curve and the x-axis. Okay, so I just wanted to get a quick note to kind of start bringing some of these ideas together.